Welcome to G Fun Facts Online. Deep beneath the majestic snow-capped peaks of the Himalayas, a colossal power lies dormant. This isn't myth or legend, but a tangible, immense source of energy fueled by the same titanic geological forces that forged the world's highest mountains. Today, we're exploring how a new dawn of geothermal engineering is looking to harness this volcanic power to illuminate and empower the communities on the rooftop of the world. For centuries, people in the Himalayas have revered the hot springs that bubble up from the ground. They saw them as therapeutic wonders. Now, science sees them as clues, surface expressions of a vast subterranean furnace. A confluence of new technology, growing energy demands, and a global push for clean energy is turning this ancient natural phenomenon into a frontier of modern exploration. So, how do you tap into a volcano under the world's tallest mountain range? Let's dig in. The first question is, why are the Himalayas a geothermal hotspot? The very forces that make the region so beautiful and so seismically volatile are the same ones that give it this incredible energy potential. It all started about 50 million years ago, when the Indian subcontinent began its relentless, slow-motion collision with the Eurasian landmass. This ongoing geological drama is what thrust the Himalayas skyward, but deep beneath the surface, that same collision creates a veritable cauldron of heat and pressure. As the Indian plate dives beneath the Eurasian plate, the immense friction causes rock to melt, forming pockets of magma that can reach temperatures over 1,000 degrees Celsius. This magma acts as a massive heat source, radiating energy upwards. This heat isn't spread out evenly. It's concentrated along major geological fault lines, like the Indus Suture Zone, which marks the boundary where the two plates originally collided. These deep fractures act as a natural plumbing system. Water from rain and melting glaciers seeps down, gets superheated by the magma below, and then rises back to the surface as the hot springs, geysers, and steam vents we see today. Scientists have identified several key areas with incredibly high potential. The most famous is the Puga Valley in Ladakh, India. It's considered the most promising geothermal field in the entire subcontinent. Situated right at the junction of the Indian and Tibetan plates, Puga has hot springs reaching 84 degrees Celsius, the boiling point at that high altitude. Surveys suggest a massive geothermal reservoir lies just a few kilometers deep, with estimated temperatures around 260 degrees Celsius. Another example is the Yengbakayin field in Tibet. This is a Himalayan success story. It's been generating electricity since 1977, tapping into fluid temperatures as high as 329 degrees Celsius and providing a major chunk of the power for the city of Lhasa. Nepal and Bhutan also have numerous hot springs, which hold significant potential, especially for direct-use applications. So the potential is clearly there, baked right into the geology of the mountains. But what would harnessing it actually mean for the region? The promise of Himalayan geothermal energy is a multifaceted boon, addressing some of the region's most pressing challenges. First and foremost is reliability. Unlike solar and wind, which are intermittent, geothermal power plants can operate 24 hours a day, 7 days a week, providing a stable baseload of electricity. This is a game changer in the Himalayas, where long, harsh winters can cripple other renewable sources. Hydropower, the traditional backbone of the region's energy, often sees its output plummet in winter when rivers freeze. Solar is great during the day but requires expensive battery storage for the night. Geothermal is immune to these seasonal swings, offering consistent power year-round. This reliability is vital for powering remote communities. Many Himalayan villages are completely off-grid. Extending the national power lines is often impossible due to the terrain. These communities are forced to rely on expensive, polluting diesel generators, and the fuel supply can easily be cut off by landslides or heavy snow. A project like the proposed 20-megawatt geothermal plant at Puga could save an estimated 3 million liters of diesel every single year. Geothermal offers a decentralized solution, allowing small-scale power plants to provide electricity directly where it's needed, improving quality of life and bolstering energy security. But the benefits go far beyond just keeping the lights on. The direct use of geothermal heat could be a powerful catalyst for economic development. In the frigid Himalayan winters, geothermal energy can be used for space heating. A successful pilot project in Chumatang, Ladakh, already demonstrated this, maintaining a constant indoor temperature of 20 degrees Celsius and dramatically improving living conditions. It can also revolutionize agriculture. Geothermal heat can warm greenhouses, extending the growing season for high-value crops, and boosting food security in these high-altitude deserts. It can be used for crop drying, soil heating, and even warming water for fish farms. A new project in Dirang, Arunachal Pradesh, is set to power fruit, nut, and meat drying facilities, creating new livelihoods. Then there's tourism. The natural hot springs are already a draw for their therapeutic benefits. Developing them into well-managed spa resorts and wellness centers can create a sustainable source of revenue for local communities. And finally, geothermal energy has a tiny environmental footprint compared to the alternatives. It produces minimal greenhouse gases, and the land required is much smaller than for large-scale hydropower dams. While hydropower is renewable, building huge dams in this geologically fragile and seismically active region can cause habitat destruction, disrupt river ecosystems, and displace communities. Geothermal offers a much more benign alternative. So if the potential is so immense, and the benefits so clear, why aren't the Himalayas already dotted with geothermal plants? The answer is that harnessing this energy is a Herculean task, filled with unique and formidable challenges. The first obstacle is the sheer tyranny of the terrain. The rugged mountains and high altitudes pose massive logistical hurdles. Just transporting heavy drilling equipment and construction materials to a remote site on narrow, treacherous roads prone to landslides is a major undertaking. The thin air at high altitude also affects the performance of machines and the productivity of workers. Then comes the drilling itself. Drilling for geothermal energy in the Himalayas means boring into some of the hardest, most abrasive rock formations on Earth, like granite and gneiss. This leads to rapid wear and tear on drill bits, making the process slow and incredibly expensive. This is where innovation becomes crucial. Engineers are developing advanced drill bits, made of materials like polycrystalline diamond. They're also exploring entirely new methods, like plasma drilling, which uses electrical currents to vaporize rock, or hybrid techniques that combine rotary drilling with water jets to fracture the rock more effectively. And all the downhole equipment, from sensors to electronics, has to be able to withstand the extreme temperatures of a geothermal reservoir, which often exceed 200 degrees Celsius. Beyond the engineering, there are serious environmental and social considerations. The Himalayas are an ecologically fragile and culturally sensitive region. One major risk is the contamination of surface and groundwater. The geothermal fluids brought to the surface contain dissolved minerals, sometimes including elements like arsenic. An accidental release of geothermal fluid into the Puga stream in 2022 highlighted this risk and temporarily halted the project. The solution is to use reinjection wells, which safely return the cooled-down fluids back into the underground reservoir after their heat has been extracted, creating a closed-loop system. There is also the issue of induced seismicity. The process of injecting and extracting large volumes of fluid can potentially trigger minor earthquakes. While the risk of a major event is considered very low, it requires careful monitoring in a region that's already seismically active. And crucially, these projects must not come at the expense of local communities. Geothermal plants, even with a small footprint, can impact traditional land use, like grazing lands for nomadic communities, such as the Changpa people in Puga. It is absolutely vital to engage with communities from the very beginning, address their concerns, and ensure they share in the benefits through jobs, better infrastructure, and other mechanisms. Finally, there's the financial hurdle. Geothermal projects are extremely capital-intensive, with most of the cost and risk front-loaded in the exploration and drilling phases. You can spend millions drilling a well, only to find it's unproductive. This risk can scare away private investors. This is why government support and international collaboration are so important in these early stages. Despite these challenges, pioneering projects are already underway, turning this dream into a reality. India is at the forefront. In Puga, Ladakh, the Oil and Natural Gas Corporation is developing a 1-megawatt pilot power plant, with plans to eventually scale up to 100 megawatts. The project is a collaboration with Iceland, a global leader in geothermal, and aims to provide 24/7 power to the remote Changthang region. In nearby Chumathang, a direct-use heating project, created with partners from Norway and Iceland, has already proven its value. And in a huge breakthrough in northeast India, a team successfully drilled the first geothermal production well in Dirang, Arunachal Pradesh, in 2025. This project will use its 115°C water for direct applications, with the potential to make Dirang India's first fully geothermal-powered town. Across the border, China's Yangbajian field in Tibet serves as a long-running proof of concept, showing the long-term viability of Himalayan geothermal power. Meanwhile, Nepal and Bhutan are emerging frontiers. Nepal is assessing sites like Tatopani for small-scale power generation and tourism. And Bhutan, the world's only carbon-negative country, is collaborating with the World Bank and Icelandic experts to assess its hot springs, looking to diversify its energy away from being solely dependent on hydropower. This theme of international collaboration is key. Countries like Iceland and Norway are providing vital technical expertise, training, and financial support. These partnerships are accelerating the pace of development and ensuring it's done in a sustainable and responsible way. The journey to unlock the full geothermal potential of the Himalayas is just beginning. The future will likely involve a mix of technologies, large power plants in high-temperature zones like Puga, combined with smaller, more nimble binary cycle plants and direct-use heating projects everywhere else. It will involve hybrid systems that integrate geothermal with solar for maximum resilience. And it will require strong government policies that incentivize investment and ensure communities benefit. As the projects in Puga, Dirang, and elsewhere move from pilot to commercial scale, they are writing a new chapter for the roof of the world. Harnessing the volcanic power of the Himalayas is more than just an engineering feat. It's a symbol of human ingenuity working in harmony with the powerful forces of nature. It's a promise of a brighter, warmer, and more sustainable future for the communities that call these mountains home. By tapping into the Earth's fiery heart, the Himalayas are poised to become a beacon of renewable energy innovation for the 21st century. Thank you for listening to Fun Facts Online.